So let's just kind of start at the beginning of the text and just walk through it, because that's what we've been doing in the class anyway. So, broadly speaking, we started out with some fundamentals, talking about voltage and current and resistance and what kind of circuit elements there are, the basic ones, capacitors, inductors. We talked about loading the circuit, voltage sources, the ones that are ideal, ones that are I guess more real or realistic, better at modeling real sources. We talked about circuit analysis, so that we got a little bit, before this we were like, oh yeah, we know Ohm's law, we know KVL, we know KCL, we know these things are true, but it's hard to put them into practice on a given problem because we can just write down a bunch of equations and then what do you do with them? So we got more serious about that in Chapter 2, doing circuit analysis. We developed a specific method that included solving differential equations to find the solution. And then in Chapter 3, we switched gears and we said, okay, let's use this concept of impedance and just consider the steady state of the response. So in Chapter 2, we included the transient and steady state responses of the circuit. But in Chapter 3, we were focused on steady state. And in particular, we were interested in sinusoidal or AC sources. And we used these impedance methods to solve for the output in steady state when you had an AC input. And one of the I guess key advantages was that we didn't have to solve a differential equation in the Chapter 3 methods. The two disadvantages were, first of all, we don't get the transient response, and second, we have to deal with complex numbers and phasors. So that was the other sort of downside to it. But it was quite nice. And then we moved on to nonlinear and multiport elements, and this is where the elements got a little bit more involved, right? But we still have elemental equations for each of them. The analysis when they're nonlinear circuits, when there are circuits that have nonlinear components in them, can't use the impedance methods, unfortunately. But if you're using linear approximations, you can do a lot of analysis still relatively easily. You can come up with linear differential equations or algebraic equations to solve, which is nice. And we learned some special applications of some of those. So like with Mosfets, we could drive a power-hungry load with a variable source that didn't have a lot of power behind it, but they sort of acted as a gate for a powerful constant source. So we learned about those. We learned about op-amps. We learned about transformers, diodes. So there's like a lot of good stuff in that chapter, and that's all we've done. So this is the bird's eye view, but it's it's like 4 different categories, and like the first stuff was sort of fundamental stuff. So really, it's just like 3 things that we moved on to that we still need to be able to do. So the basics, talk about how to combine resistances in series and in parallel. Voltage dividers, remember they came into play early. We had voltage dividers just with resistor circuits, right? And we solved for what the voltage across one of the resistors would be given a series orientation of several resistors. And that was a really useful analytic technique, right? Just having that one circuit analysis allowed us to, short circuit in a way a lot of other analyses. We didn't have to do the whole circuit analysis. When we saw a voltage divider, we could just use that result. So that was nice. Capacitors are where we first learned about differential equations coming into these dynamic system models, right? So resistor elemental equations are algebraic. The Kirchhoff's laws, current and voltage laws, KVL and KCL, are both algebraic. So it wasn't until we introduced the capacitor that we started to get differential equations, right? And then we could solve the differential equations that emerged from the circuit analysis. We also introduced inductors as well, which also have a derivative in them. So more differential equations. And then we decided to get more systematic and do a circuit analysis methodology. First, we defined the sign convention, and then we defined this 6-step process of analyzing a circuit using I've often called this Chapter 2 methods, but essentially what this is looking at transient and steady state response for a circuit. And this will apply, this applied again in Chapter 4 when we looked at nonlinear circuits. This applies all the time. The trouble with it is that if you have nonlinear systems, you have nonlinear differential equations, or algebraic equations if you don't have any capacitors or inductors in there. So you've got a process that takes you, from the few laws that the sort of the elemental equation laws, which Ohm's law is one. But then the elemental equation for a capacitor is another, elemental equation for an inductor is another. So those, KCL and KVL. So you just sort of walk through and you apply those. And then you have to simplify this kind of complicated system of equations, right? And you want to get it down to a point where you're solving a differential equation that you can sink your teeth into. On the exam, be prepared for first and second order by hand. Be able to do first and second order systems by hand, even up to third order. But I'm not saying that. So the second order, one of the second order examples that you guys had in your homework was very involved. It had a sinusoidal input, and it had a second order system, and it was including the transient analysis. So it wasn't just the steady state response. So that was a very involved problem. I would not expect you to be able to do that on an exam, because that would just take too much time to just work through all of the algebra, right? So that's not really what I'm going for on the exam. But be prepared to know how to do all those steps, because I might ask you a specific part of how to do a second or third order system, but something that doesn't require a lot of algebra to go through. Because I don't want you guys to write like 4 pages worth of algebra. That's stuff that I assume you already know how to do. So, true or not? So, and then we started looking at different types of circuits, AC input circuits, and then we broke down into the transient response and the steady state response in this figure, right? So the transient response happens during the first, if you look at the time constant as being something that's not just for first order systems, then you can think of all of these system responses that are stable, at least, having a time constant decay, okay, an exponential decay. So this transient part of the response has that exponential characteristic where it's settling down to some new value. And it's not a sharp transition. I mean, this sort of shows it as being a sharp transition. But this is the transient time when the initial condition is still affecting the signal or the output significantly. And then once you reach a fairly stable situation where you're just repeating the same waveform over and over again, that would be steady state. Of course, an exponential only goes to 0 in the limit, so it's more of a qualitative difference than a quantitative difference. It's not this sharp transition at like a certain number of time constants. Like we often say, oh, well, after 5 time constants, it's steady state. But there's a little bit left. It's like within 1%. 6 time constants is then like within like 0.1% or something. And like it gets closer and closer, but yeah. So that was important. Steady state circuit analysis. So then we talked about representing a signal in terms of complex numbers, right? A sinusoidal signal in terms of a complex number. So we introduced the phasor. We talked about how if you have a sinusoid with an amplitude and a phase, then you can just take those two as the most important. Because in steady state, if you put in a sinusoid to a linear system, then you get out a sinusoid, and the sinusoid has a new phase and a new amplitude, but that's all that's changed. It's still the same frequency. That is not true of a nonlinear system, though. So you put in a sinusoid. I mean, in our example, we showed that because you put in a sinusoid in our example, and we got out this weird clipped thing, right? It would go positive, and then it was 0. And it would go positive, and then it was 0. So you just like got all these, this like hump, flat, hump, flat. That is not a sinusoid. So nonlinear systems don't give you, in general, a sinusoid back out when you put in a sinusoid. And that's, in Chapter 3, we're saying, well, there are a lot of systems that aren't nonlinear. There are a lot of linear systems or approximately linear systems that if you put in a sinusoid, return a sinusoid. And that's this analysis. So this sort of phasor notation, and then I went back and I did this extra one where it talked about how to go from trig to the polar phasor form to another complex number representation, which is the rectangular form, and back. You can remember if you're doing multiplication or division, typically the phasor polar form is the one that you kind of prefer. And if you're going to do addition and subtraction, usually the rectangular form is easier to work with. So depending on which operation we're doing, we switch back and forth. And so this gives you the formulas for going back and forth. Impedance then we talked about. And then we started to do, we modified our methodology, right? So the Chapter 2 methods required a certain process, and the Chapter 3 methods are actually very similar. So we have a lot of the steps being exactly the same, except that instead of writing the elemental equations in their original form, we can use their impedance form, which is generalized Ohm's law, or every one of these is V equals IZ, right? So you write the elemental equations, but they have impedances this time. Steps 4 and 5 are the same, KCL, KVL, those are still true. But now in step 6, when you need to solve for whatever you're looking for in the problem, like the output voltage or the voltage across a certain element, or the current through some element, your equations are algebraic, which is nice. You don't have to solve a differential equation. So that's the big payoff for doing the impedance methods. So we talked about that. We talked about how you can do a voltage or a current divider with impedances as well, and we wrote those down, did an example, and that was Chapter 3. And I added several problems to the end here, which I think would be good practice to go through. And then finally in Chapter 4, we said, okay, what about a transformer? It's got 2 ports now. So instead of just having 2 wires sticking out of it, it's got 4 wires sticking out of it. And transformers allow us to trade off voltage and current for a time-varying signal, right? For typically an AC signal. So that was a useful component to learn about. And what was nice is that it pretty much it just introduced its own elemental equations. Of course, when it's got 2 ports, it's got to have 2 elemental equations. And so we have 2 of them, but they're algebraic. So that turned out to work nicely for us. And what's nice about these transformers also is that they're mostly linear devices, and this approximation of them is definitely linear. So we're able to use the impedance techniques with transformers, unless there's another element in there that is nonlinear in that same circuit. And also, I guess another case where you wouldn't be able to use that is if you were interested in the transient response as well, right? So if you're interested in the transient response, there's no replacement for going back and solving the differential equation. You have to. You can't use impedance methods if you want to know the transient response. Okay, then we talked about diodes, which now we got to our first nonlinear element, right? 1 port, so it's got 2 wires sticking out of it. And the main idea is that current's only flowing in one direction, right? It's going to block current from flowing the other direction. And that is a very nonlinear thing. And this nonlinear diode model is pretty good. But it doesn't even have the breakdown voltage as part of it, right? Because remember, if you go to a very large negative voltage across a diode, it will eventually flow current in its reverse bias direction, which is not what you typically want unless you're using a Zener diode. So that's typically not what you're looking for. So even the nonlinear diode model doesn't have that breakdown voltage as part of it. So we start to, even the nonlinear one is an approximation. Then we go to a further approximation, which is a piecewise linear model. And the piecewise linear model is an ideal diode, which is on if there's positive voltage across it, and it's a perfect conductor. And if there's negative voltage across it, it's off, and it's a perfect insulator. So it has an ideal diode and a voltage drop, and then a resistance. So when you get above a certain voltage across it, you're going to have this linear relationship between voltage and current. And that's what we talked about at the beginning today about how to approximate RD, is we're trying to make that straight line approximate an exponential in a certain region as well as we can. It's not perfect. Piecewise linear diode model, this is what the current relationship is, the voltage current relationship is. So this is the elemental equation, right, for the diode. But it's piecewise defined, and that creates kind of an issue for us in terms of our analysis, right? And that's why we use the method of assumed states, which is to say we march through and we say, okay, I'm going to assume that this one's on, this one's off, and this one's on. And then you do the analysis, but when you encounter a contradiction in your analysis, you know that your assumed states of on, off must be false. So you don't necessarily know which diodes are wrong and which ones are right, but the ones, if you can boil down your contradictions to contradictions in the direction current would be flowing or the voltage would be dropping, which is what I recommend in these steps, then you can have a pretty good guess about which ones should be flipped. So if you solve for if you've got 3 diodes in your circuit and one of them was violating the assumption, try flipping that one. That's a good guess, and try again. So this method is pretty effective, and we use that in all its glory. But so notice that. So I did an example. There's always this struggle, because when I do a complicated example, it seems like it's hard to get like the simple stuff. So I give you guys some simple homework problems with diodes that have just DC sources and don't have this sinusoidal input in them. And it's way easier in that case. But I did an example that was actually sinusoidal input, which is much more complicated. There's always a tension between like doing the simple example in class or doing the complicated one. I swear when I do complicated ones, my student evaluations always come back that I should do simpler examples in class. And then when I do simple examples in class, they always come back and say I should do more complicated examples in class. So I don't really know. I'm like trying to find a balance there, but sometimes I think I'm like, I do the simple one, and I'm like, no, they want more complicated ones. So I do the complicated one in class this time, and I think this one might have been a little bit intimidating too. So I give you guys quite a few diode problems in your homework that's due today, and you have a quiz over. And I think that especially when you're using the ideal diode model, they're pretty quick. They don't take a ton of time to do the diode problems. When you have to use the piecewise linear model, it gets a little bit more dicey. Okay, and then this is the section that I just added with how to determine the diode resistance in the piecewise linear model. Like I said, you can be really rough with this and still get a pretty good result typically. So I don't encourage you to use this sort of process like on an exam. Like you don't need to go through 10 iterations and get like a really great value of your resistance. Going through it once would be fine. Even doing a more rough estimate, just justify it. Just say, well, if the resistance was 0, then this would be the current flowing through this component. And if the current flowing through this component is this, then that would correspond to being in this operating regime. And this line would be approximately, this is the slope I need to be approximately there. As long as you justify it in some way, even if it's pretty rough estimate, it's not a big deal. So, yeah. And if I wanted you to do that, use that method, I would explicitly request it on the exam. Mosfets. I covered it just slightly at the beginning, but the idea was that if you have like a small variable signal, you can connect it to the gate. This is our typical application, but I mean other applications for MOSFETs we didn't really discuss. Mainly, we want to be able to take like a microcontroller or something that has a variable signal that we can control, but that can't supply a lot of power, and we want to supply a variable but powerful supply to like a motor or some power-hungry device. So we would be able to use a sort of a fixed large source with power behind it, and use this gating scheme for a MOSFET to drive this power-hungry load. So that's mainly how we discussed the MOSFET. Understanding, the basic operation of it, that it's very nonlinear, that we don't really want to be in the triode region, how to test for when you're in the triode region versus when you're in saturation versus when it's in cutoff. Those are all things that you should be able to do for the exam. This example and your homework problem were pretty similar. So hopefully, you see that this is kind of the application I'm looking at for this for you guys. I'm trying to get you guys to understand. So, expect at least like some questions about how you would do this. And then the last one was the op amp, right? So op amp was nice for several reasons, one of which was that we can do a similar sort of thing where we can supply power using a small signal and then another power supply. But one of the things that was really nice about the op amp was that although it is a nonlinear component, it can operate in linear mode relatively easily. Like it typically will be operating in linear mode as long as you use this negative feedback which we discussed in terms of needing to have some connection from the output to the inverting input. And when you have that, we went through this whole argument of like why this works, but you can get a nice linear operation, and you can use it to be a voltage-controlled voltage source that's linear. So you can look at the MOSFET as being a voltage-controlled current source, but it's very nonlinear, which sucks. What's nice about the op-amp is that it's linear. And so if you, as one example, I didn't get into it during the lecture, but the one example of why a linear amplifier is very useful is that you don't get distortion in a sinusoid. So I talked about how if you put a sine wave into a nonlinear system, you probably aren't going to get a sine wave back out, right? So say that sine wave, imagine, so in your, probably in 315 class, you guys have talked about Fourier series a little bit, yeah? So the idea being that a signal is composed, any periodic signal is composed of a bunch of sinusoids, okay? You can approximate it by just being a sum of sinusoidal terms. Now, that idea mixed with the idea of superposition in linear systems, which we haven't talked about much, but the idea is that if you put in a sinusoid to a linear system, you get out a sinusoid. And if you have a bunch of sinusoids that are summed up in the input, you can think of a periodic signal in the input being a sum of a bunch of sinusoids, then the output will also be a sum of sinusoids with just different amplitudes and phases. And you can get distortion with a linear system too, depending on the frequencies of those components. But your distortion with a nonlinear system is going to be way, way more drastic. Okay. So if you were to use, if you were to think of the signal as being like your voice, and it's being recorded, and then being played back with an amplifier that's non-linear, it could very much distort what you sound like, okay? So like audio fidelity would be an example of the type of thing that you would want to use a very linear amplifier for. If you want to increase the power of the signal, you want this signal to be a louder signal. You want to use an amplifier that's going to be linear. If it's non-linear, it's going to introduce distortion. It's going to sound weird. So that's part of why linear amplifiers are so important, because when you put something into it, usually you get something that looks like what you put in, but just bigger power behind it. So linear amplifiers are great, especially for situations where a little bit of distortion is a problem. Another situation where distortion is a problem is in other measurement systems. So if you're measuring things, so this is related to 315 as well, if you're measuring things, you are wanting fidelity to the original signal. But if the original signal is small, you have to amplify it. But when you amplify it, if you distort it, you don't have a very good measurement of your original signal. So linear amplification is very important. So op-amp does a lot of good stuff for us, including nice linear amplification. So that's all that's all we covered, right? There's also, I don't really have time to go through problems, but I think I've done examples of most things, and I'm happy to, if you guys are like, really want me to do, I think somebody asked for an impedance example. If you guys send me like a specific problem you guys want me to work out, like I'll record a video this weekend, and it could just be like an example problem of that. Just let me know. Happy to. Yeah. Otherwise, open notes, your own notes, the notes that I give you. You can bring a calculator, but not your books. So no books, no phones, No cheating. I had somebody cheat on a final exam last year. Oh, that sucked. Don't. Yeah. Well. Yeah. I know. So it's really something that I don't want to see. So just be really careful to have your integrity, and then you can bring in your homework solutions that you wrote out. So that's fine. Don't bring in my homework solutions. Yeah. So that's fine. You can bring that in. Your own work in any way is fine to bring. So if you write out a note sheet specifically for this exam, that's fine. Bring that in. Whatever you want of your own notes, you can bring. You can work out example problems for yourself if you want to. That's fine.